Alright, so basketball, this is the lecture that you missed tonight. I start off the class with an announcement about current events, and most people haven't done current events. And so what you are looking at is a presentation schedule. If your name is on here, you need to be prepared, and I am going to hold you accountable. And so presenting on Monday, we're going to go in this order that you see here. So Dustin, Kevin, Ned, Greg, Keaton, and Cruz had actually signed up to present on Monday, so they get dibs first. We're then going to go through the rest of the class just until time is called in this order. And so the people down here in the brown and the blue are people who had signed up but then either procrastinated or got delayed and needed to move theirs back, and so you get second priority. Lastly, over for presenting current events on Wednesday, I've got Jalen, Will, Kevin, Jake, Kamani, and Lance and Patrick. And so if you're on that list, you need to come prepared by Wednesday. If you are not able to be in class that Wednesday because you're going to be out of town, you need to let me know, and you need to send me your paper by Wednesday. I will let you present after that, but if I don't have your paper by Monday, right, if your name is on the Monday list, or Wednesday, if your name is on the Wednesday list, then there is going to be no other opportunity for you to make that up, so you need to be diligent about it. Please email me, call me if you have questions on that. Other than that, our topic tonight is populations, and specifically human populations. And so we've studied animal populations, and we know that animal populations have what we call a carrying capacity. Carrying capacity is just that nice, happy number that an environment can sustain due to the resources. And so somewhere in the middle here with this red line is the carrying capacity of both the snowshoe hare and the lynx. We also know from our previous chapters that when a population goes way over the carrying capacity, it's called an overshoot. And when they go way under the carrying capacity, it's called a crash. The interesting thing about this, though, is that we don't really see human populations going through this motion of overshoot and crash and overshoot and crash and overshoot and crash. The human population does a much different thing. And so in class, I had people take a guess of what the human population graph is if you were to do population on the y-axis over time on the x. And so you've got population here. There we go, population over time. And people made predictions. And so if you want to pause the video here and make a prediction, I encourage you to do that. What we see the human population actually doing over time is this. And so we see that for most of human history, right, from 8000 BC to about 1000 AD, right here, the human population stayed relatively constant. It increased a little bit and kind of had its ups and downs, but it was pretty constant. We did see a big growth right around 1000 AD. And then the bubonic plague, or the Black Plague, actually had a noticeable impact on the world population, and you can see that right here. The more interesting thing is what happened after the Industrial Revolution. And so the Industrial Revolution is when we gained the ability and the technology to mass produce things. We also had huge leaps in science at that time, as well as medicine and agriculture. And so all of these things, technology and industry and agriculture, made quality of living for people a lot better. We started to see people living longer and frankly having more babies because it was sustainable, because they had the resources to do that. And since that time, the human population has grown exponentially, as you can see. A few important numbers here are that currently in the world there are 7.046 billion people, right? And you can see this up in the left-hand corner. The average life expectancy worldwide is 69.92 years, and our population is growing at a rate of 1.2% annually. There's this rule in biology and biological sciences about things that are growing exponentially, and it's called the rule of 70, and I do expect you to know this. And the rule of 70 is that for things growing exponentially, I can find the time it takes for that population to double. And so I can do that by taking 70 years divided by the growth percent, and in the case of the world population, it's 1.2%. And when I do that, that gives me how many years until the world population doubles. And so I want you to get out a calculator and go ahead and figure out that number, and that is going to be an important number that you will see again. And again, this is called the rule of 70. And so what should we do? In class, we had the proposition of not making medicine anymore and letting people just die like they should, and that would decrease world population. We also had the suggestion of telling people that they can't have children. However, neither of those are moral solutions. We can't do either of those. It's unethical. And so I love this quote that for every complex problem, there is an answer that is clear, it's simple, but it's also very wrong. And so we experienced that in class tonight. The issue of world population growth is a complex one, and there's not an easy solution to it. However, I'm not here to tell you that this is a good thing or a bad thing. There are two views on the subject, and so some people believe that population growth is the ultimate cause of poverty and environmental degradation, right? That we have these issues because of growing world population, that we've got more people and that's causing these things. On the flip side of that, others argue that poverty, environmental degradation, and overpopulation are all symptoms of something else that's deeper in our social fabrics. Some people even think that increasing the world population could be a good thing because more people means better economic markets, more workers to make more goods, and better economies overall, which could improve the situation of poverty in some places. And so what I want you to do is take a minute and think about all of these issues that we've covered in class so far. We've talked about pollution, habitat destruction, climate change, use of natural resources like water and trees and soil, mining and industry and the things that we get out of the earth. We've talked about solid waste, particularly municipal waste. And we've also talked, and it's been a while, but we have talked about endangered species and biodiversity. And so what I want you to do is take a minute and kind of brainstorm. If the world population is increasing, how is that going to affect pollution? How is that going to affect use of natural resources? Amount of solid waste produced, our mining and industry? How is that going to affect habitat destruction, climate change, and endangered species? And so what I'd like you to do is come up with your own kind of result for each one of these as a result of world population increasing. You're going to see this in the form of an essay question and being able to talk about that. If you struggle with this, come see me, email me, call me, happy to help you out with that. Alright, so how are we actually affecting the environment? We've got this little formula to help us out, and it's the IPAT formula. Okay, the things that I really want you to know are what each letter, each variable in that formula stands for. And so the I is for environmental impact, the P is for population, A is for affluence, and affluence is in so many words how rich somebody is or how much money they make. And so people that live an affluent lifestyle oftentimes have a lot of luxuries, and so we in America, actually compared to the rest of the world, have a very affluent lifestyle. We consume a lot of things. And then lastly, the T is for technology. Right? And so technology would be things like cars or industry, new inventions, things like that. And so what we see is in the IPAT formula, as population, P, increases, so does the environmental impact. As affluence increases, so does the environmental impact. And as technology increases, so does the environmental impact. However, we know that a couple of these aren't true. So namely, affluence does not always have a bad environmental impact. And technology does not always have a bad environmental impact. Okay. In affluent societies or richer societies, often people are more educated, and we know that education actually decreases birth rates in women. And so that aspect of an affluent society, it actually does decrease world population. However, in affluent societies, we are very consumer heavy. We buy a lot of things and we consume a lot of things, which require Earth's resources. It was also mentioned that in affluent societies, because of education, maybe we would be more inclined to know how to reduce our impact. I did ask the question to the class, well, okay, we're in an environmental science class. How many of you have actually changed your lifestyle or some things that you do because of what you've learned in here? And nobody raised their hands. And so while we do have that education at our disposal, is it actually changing the choices that we make? And oftentimes the answer is no. But we do see that affluence and education impact birth rates in women, for sure. The other issue here is technology. Technology is not always a bad thing. A lot of the technologies we have do pollute and do impact the environment negatively by carbon emissions and things like that. However, there are some new technologies that actually reduce our impact on the earth, and so the Prius is a great example of that. It is a car that does have carbon emissions, but it's far, far fewer. And so we have technologies that still allow us to live our affluent lifestyles, right? But they don't have as great as an impact on the environment as our current technologies. Another good example of technology not having a negative impact would be like windmills or geothermal energy that we talked about in the last chapter. All right. So we've got the IPAT formula. The other thing that we can look at is what is called our ecological footprint. And our ecological footprint is a vocabulary word that you need to know. And an ecological footprint is measured as a land equivalent of our consumption choices, right? And so the things that I use every single day, paper products and plastic products and things with rare earth metals, all have an impact on the earth, and they all require some amount of land use. And so what we look at is the consumption choices of an area, and we equate that to, okay, well, how much land is required to produce the goods that they are consuming. Page 82 in your book has a really great example of this. What I'm about to show you, here we go, is a comparable graph to page 82 in your book. And so we see that the more affluent countries, right, like the United States and Belgium and Denmark and the United Arab Emirates, all have a very high ecological footprint. It takes a lot of land to produce the goods that we consume. Consequently, less affluent countries, right, like the Czech Republic, they use much less land to produce the resources that they consume, and thus they have a smaller environmental footprint. And I've already mentioned this, but technology also has the ability to decrease our impact on the environment. And so some of our current technologies are not great for the environment, but we do have a lot of good options too. And so some examples of that would be like cars and machinery that produce less pollution than the technology that we have currently. Developing more efficient ways of producing technology or recycling old technology. So if we can find a way to recycle rare earth metals, then our cell phones won't cost as much and they won't have as big of an environmental impact. And then another good example of technology decreasing our footprint is when we use technology to increase food supplies, and so we can get more crop for our land use. We can get more profit out of that land use, and that's a great example of technology decreasing our footprint.